Now let's consider any gas. In this case, we can write the energy per molecule as contribution from translational kinetic energy of the center of mass and other components. So I'm going to talk about the energy of a molecule in any gas. The energy per molecule can be written as a sum of terms that include the translational kinetic energy of the center of mass and other terms that include vibrational and rotational motion with respect to the center of mass. So this epsilon k is kinetic energy. It's the translational kinetic energy per molecule. Now we can write this energy epsilon k as in the previous case 1 over 2m mass of one molecule px squared plus py squared plus pz squared. And the other term in the energy, epsilon prime, may involve center of mass position. So just like what we said in the derivation of equipartition theorem, we're isolating the contribution from momentum, linear momentum. It may include coordinates and momenta that is describing rotations and vibrations with respect to the center of mass. But it does not include center of mass. There is no center of mass momentum P contribution to this energy term epsilon prime. So looking at epsilon x in the kinetic energy, I have 1 over 2m Vx squared. So when I take its mean value, it's going to be 1 over 2m Vx squared mean value, which is mean value of px squared divided by 2m. 2m is just a constant. So according to equipartition theorem, this is supposed to give me 1 over 2 kt. So I can see that the mean value of Vx squared then should be kt divided by m. And if you look at the standard deviation in Vx, we have square root of Vx minus Vx bar square bar. So since we have the mean value of Vx from Maxwell's speed distribution to be 0, the standard deviation in Vx is going to be equal to square root of Vx square bar. And since Vx square bar is kt over m, we will find that the standard deviation in Vx is going to be square root kt over m. So this calculation allows us to account for the standard deviation in Vx. So most probable values of Vx will lie in this region 0 plus or minus square root kt over m. And the mean value of the kinetic energy contribution, once again, because it has three independent terms, px, py, pz, quadratic terms. So this will give me, just like in the monatomic gas, ideal gas case, 3 over 2 kT. This is due to equipartition theorem. So as you can see, this theorem is quite useful in calculating the mean values of energy and the velocity components or speed as well. So you can take this discussion and you can do further analysis to calculate the standard deviation of v as well as the components of the velocity. Alright, so we have considered any gas, and basically the energy per molecule has a contribution that includes quadratic terms in the linear momentum of the center of mass. That is 1 over 2 mpx squared, 1 over 2 mpy squared, 1 over 2 mpz squared, and then it has terms due to vibrations and rotations with respect to center of mass. These terms may involve center of mass position, coordinates, and position coordinates and momenta describing this motion. Therefore, we have the center of mass momentum isolated in one term, which is for the x component of momentum 1 over 2 mvx squared. Its mean value, according to our equipartition theorem, is 1 over 2 kt. So that allows me to calculate the standard deviation in Vx as well, because Vx square bar has to be kt over m. And because the mean value of Vx is 0, this comes from the Maxwell velocity distribution, we must have the standard deviation in Vx to be square root kt over m. And the mean value of the kinetic energy term will still be 3 over 2 kt, because it's not any different from the case we have discussed for the monatomic ideal gas.